Hey guys, your boy Chill here. Welcome back to Hardware 3D. Today's topic is alpha blending / alpha testing. Now this is something that is pretty simple to understand in principle, but when you get down to the little details and the corner cases, it can be really complex in practice. First things first, let's take a look at the scene. It's what we got at the end of the last video. And as I showed you there, these petals, they look dumb. And this is supposed to be vines. Does not look like vines. Looks like some kind of goop, right? It's not good. Why is it not good? Well, let's take a look at the assets for those pieces of geometry. If we look at the models and what is it, Sponza? Look at the textures here. We can see here's the vase plant, and here's a normal map for it, and specular. And what we see here is there's a mask. So it's not meant to use this entire texture. It's meant to mask out parts of it. And in order to draw with a mask, here's the plant, here is the thorns, here's the thorn mask. If you look at the texture here, the geometry that is used to draw the plants and stuff, it's just basically a square, right? So if you just draw it as a square and you texture this, lots of it are going to be white or whatever color this is here. I say whatever color because this might actually be alpha, and it's just rendering the backdrop as white. Let's take a look at it in Photoshop. Yeah, in Photoshop we see that it has an alpha channel here. And so the alpha for these parts here is going to be about 255 around there, and the alpha for these parts is going to be about 0. And that tells the opacity of any particular pixel in the texture. So the geometry is a square, and you only want to draw pixels if the pixel in the texture has an alpha value. Now I've already covered alpha blending, the basic raster operation there, in the intermediate C++ series. So you can search the wiki for alpha blending and you'll find a video that goes over that in some depth. But to recap, colors are generally stored as 4 components. You have the RGB, and there's the 4th component, A. That is the alpha value. We haven't been using it up until now in Hardware 3D. But when you want to draw, when you want to write some pixel to the destination surface, the render target, what you do is, instead of just copying over this one, you can blend between the two. And it's just a simple linear interpolation. There's no difference here between, interpolating between 2 normals and interpolating between, 2 color values here. And the controller that controls how much you take of each color is the alpha value of the source. It's controllable. You could use it as the alpha value of the destination or some combination of the two. But generally, the source alpha controls how much of the source RGB is used, as opposed to how much of the destination RGB is used. And again, it's just a simple lerp. That is the executive summary. If you need more than that, then you can go back to intermediate C++, you can search the wiki, and you can get a more detailed explanation there. Now, in order to render our material taking into consideration alpha, we need 3 things. First, we need a texture with some alpha information, an alpha channel that isn't just all 255s. And we have that already. The second thing we need is we need our pixel shader to read that alpha value and to output that alpha value in the 4-channel vector that it outputs for the color. The third thing we need is we need to set the rasterizer blending state to tell it to blend using the alpha channel in the way we want it to. So like I said, texture is already taken care of. The second thing, the shader, is pretty simple. We're just going to sample a 4-component color vector from the diffuse texture, and then when we add all these things together, we're going to do our normal calculation of all the different lighting components, and we're going to combine that. That'll be a 3-component vector RGB, and we're going to combine that. The 4th part is just going to be the alpha from the texture, just going to be passed through as is. You can see here before we were just using a constant value of 1 for the output alpha. Although it wouldn't have mattered because we weren't setting the blend state. So this could have been anything and it wouldn't have affected the output. But anyways, now we're setting it to the actual alpha channel that exists in the loaded texture. Now to set the blend state on the rasterizer, or I believe it's the output merger, anyways, to set the blend state on that stage of the pipeline, you're going to need, you know, some interface stuff, Direct3D, and in our system, like everything else, we model that with a bindable. So we're going to create a new bindable. We'll call it the blender. And it's going to wrap around an ID3D11 blend state. And it's also going to have a piece of data here, member variable bool blending, which will control whether the blend state will be blending enabled or blending disabled. And then when you create this thing, you pass in the bool telling what kind of blend state you want to create. So some objects, they're going to want to disable blending because they're not using it, and it does, you know, consume more GPU performance. And things that use the blending are going to have this set to true. Then we look into blender.cpp, and it's not that complicated, I don't think. It's like all the other Direct3D stuff. You start creating it by creating a descriptor, and then you fill that descriptor with the configuration information. So if blending is true, then we are going to create one with blend enabled equal to true. The source is going to be the alpha. The destination blend is going to be the inverse of the alpha. That's a basic alpha blending or just linear interpolation formula. And the blend op is going to add between the two things. Source times alpha plus destination times the inverse of the alpha. Now these options here allow you to blend the alpha values as well together. But we're not blending alpha values, so we're just going to set that to 0. And this op doesn't matter. We'll set it to add. It doesn't matter what it is. Finally, there's a mask that we could use, but we're not going to use it, so we just say enable all, allow it to write to everything. You would really only change this for special effects. You might only want to write to the green channel or the blue channel or the blue and green, whatever. Doesn't matter. We're not going to be touching this in any foreseeable future. And if the blending was set to false, then we're going to set blend enable equal to false, and we'll still set the color, the right mask to write to everything. And then you create the blend state, the descriptor, and you pass it in the PP to be filled, and there you go. And when you want to bind it, you say it's the output merger, so you do OM set blend state, give it the pointer to the blend state, you pass it null pointer, you pass it all Fs. These ones you probably won't have to change. No, I lied. This null pointer here, this could be set to a blend factor, a constant blend factor that you can use to apply a factor over the entire object being rendered, so you can like fade it out uniformly, all the pixels at once. So for example, up here in the source blend and destination blend, there are options that allow you to use the values passed in here to uniformly blend. You'll actually see that later on in this video. This last mask here is for multi-sampling. That's kind of an anti-aliasing issue, and we won't be touching that for a while now, so you can just forget about it for now. But this one we'll see a little bit later. But yeah, it's fairly simple. The base, you just bind it to the output merger. This stuff is your basic, you know, boilerplate that we need for our codec system. And that's basically it. Other than that, all I've done here is I've removed a couple of textures that aren't needed anymore. The mask, because obviously alpha channel is already in the PNG, so you don't need a separate mask texture. And I replaced the normal map for the plant with the normal map from a different model. Also edited the specular. It was just basically a copy of the diffuse, so I made it black and white. So here's what we get, and already we can see, well, this looks a little better, doesn't it? The pillar, the ivy here, it now looks a little more like ivy, a little less like some kind of goop. And we can see our flowers there. Let's take a look at the flowers. Let's take a close-up look at the flowers. What the hell is going on here? This is not acceptable. So, interesting little effect happening here. Can you guys imagine what it is? Can you put your deductive powers to work and see exactly what's happening here? So to make a long story short, we are rendering, you know, our flower. So the geometry is basically just a quad, and then we're copying pixels, the flower here, and we're leaving the stuff underneath the color as it was before, which was the floor color. So first, let's say we draw the floor. The floor is here. The black is the floor. Then we draw the flower like this. So we have flower here, and these are the floor pixels. Then we're going to draw the vase. So we draw the vase. Not getting color there. We draw the vase. And what it's going to do is it's going to do its alpha test, and it's going to say, yeah, the vase is above the floor, but the vase is below the flower. So it's going to draw like this. The alpha masking is going to prevent the stuff around this quad of the flower. The vase won't be drawn there. And so the floor will peek through here, and it's going to look very weird, and it's going to look very dumb, and it's not going to be right. There's a couple of ways you could solve this. You could change your draw order. You could use Painter's algorithm. First draw the floor. Floor is 1. Then draw the vase is 2. Then draw the flowers 3. If you do it in this order, you will get the expected result. But we know from 3D fundamentals that we don't like to do it like this. We like our Z buffer. It allows us to draw in independent order, which is great for a number of reasons. So the actual solution here, the solution that we're going to go with, is, well, we are just going to discard the pixel. Pixels like for example, this pixel here, its alpha is going to be equal to 0, let's say. So if we discard pixels with 0 alpha, we don't even allow them to make it to the output merger, then this Z value will remain the value of the floor, and then when we draw our vase, it will be allowed to draw over this part here. So we have to do an alpha test, a little bit of a branch, to see, you know, what ones we can actually draw and have their Z make it to the Z buffer, and what ones should just be discarded immediately. Oh, by the way, I skipped over something important in this change here. Let me just go over quickly in the mesh.cpp. So we do another test when we're loading our diffuse texture down here. We check to see if the texture actually has alpha channel values that are different than 255. If so, we set this flag. And then down here, outside of this if-else chain, no matter what the material combination is, every mesh needs to have a blender. And its blending state will be determined by whether it has an alpha diffuse or not. Good. Now, next one, implementing the Z test. In mesh.cpp, what do we do here? So we remove the blender. We decide, yeah, we're not actually going to do alpha blending. We're just going to do alpha testing. So, psych! Video wasn't actually about alpha blending, although I managed to sneak it in here. It actually could be implemented without it. All you do is at the very beginning of our pixel shader, we are going to sample the texture, and we're going to call a function clip. And what clip does in the pixel shader is if, well, let's look at the actual documentation. Discards the current pixel if specified value is less than 0. So you pass it a scalar value, and if that value is negative, then it just basically aborts the pixel shader, does not go any further. And that's what we're doing here. If the alpha value is at a sufficiently low threshold, let's put it at 0.1, then we're going to clip. Otherwise, we let it pass through. So now we have our transparency with alpha testing instead of alpha blending. And if we look at it, yeah, that looks pretty much what you would expect. Looks okay to me. Up here, up in here, up in here. Looks good. Zoom out, still looks good. Not bad. So, a bit of a psych there, but I wanted to show you guys just alpha blending a little bit there to see how to do it. And just because we were on a similar topic. In the future, when we actually have a model that needs true alpha blending, we'll revisit it. But let me show you something cool here. So the Phong PS spec normal map, which is the only one that we enabled the alpha test on, because that's the only ones that need it. Here I set the threshold for clipping, for rejection, to be alpha values that are less than 0.1. You might wonder, why 0.1, Chili? Why that value? Why not just set it so that anything less than, you know, full opacity, basically anything less than opaque, should be rejected? Well, let's try this out. Let's see what happens when we set it to this. Make your predictions. Okay, right now we're seeing, okay, this is a little weird. Something seems weird here. It looks like there's a lot less foliage than we had before. Now watch what happens when we get closer to it. The foliage magically appears, but if we zoom out, it's freaking disappearing. It's dissolving, mate. What the hell? Why is it doing this? Well, I could tell you, but that's not fun. So I want you to think about it. Why is the threshold, why is it dissolving like this at far away distances? Think about it. Put your answer in the comment. Either way, it turns out we need this threshold to be fairly tolerant of a little bit of alpha in there. So we'll only clip things that are mostly transparent. And that works fine for us. Although it can introduce a little bit of annoying artifacts at the edges, it's not a big deal right now. We're not going to worry about it. Now, besides the foliage, there's one more part of this model that uses that cookie cutter alpha test technique there, and that is these chains here. These chains, from a distance, they might look like they're properly modeled, but if you get up in their face, you're going to see, that's weird. They are actually textures. It's actually like a cross hatch of textures. Let me see if I can get a good view of it here. Yeah, here you can see the general cross nature of this. And this kind of technique is used, or at least was used very often for things like trees. It's becoming less and less common these days now that graphics hardware is more powerful. But you get the idea. It's not a terrible effect, but it breaks down when you look at it close. It especially breaks down when your texture doesn't have a proper alpha channel. So let's take care of that. So we remove the mask thing. We add a specular map to this guy, and the chain texture, we modify it from down here to down here. It's a little brighter. I might have actually made it too bright, but at least now it'll have an alpha channel. So with our newly spangled chain texture, now we're getting the proper transparency. So now you can see behind it, and yeah, you see. It uses this cross-hatch thing so that you can see it from either side. But look at this. Look at when I look at it from this side. The freaking chain disappears on one of these guys, see? Now you don't see it. Now you see it. Now you're seeing two of them. Why is this? Well, I mean, these things that are modeled, they're just modeled as a single, basically a single quad, right? So we have back face culling enabled. So when we look at any triangle from its backside, it's going to disappear, right? But these things, they need to be visible from both the backside and the front side. It's really the same for these flowers. If we look at the flowers from the bottom, they disappear, which is less common of a occurrence, but could still technically happen. So for these guys, we actually have to turn off back face culling to render them in, all the different situations. So let's take a quick look at the graphics pipeline again. We haven't looked at this in a while. We were just visiting the output merger. That's where we set our blending state. Now we want to set the back face culling behavior, and that happens at the rasterizer stage. So we're going to have to bind set some kind of state on the rasterizer stage. We're going to create a bindable, as we always do, to organize that, to package it up nicely. It's been working pretty nice so far. So here I just do a quick test to make sure I can get a rasterizer working. Create rasterizer.h, and it has a boolean here to control whether it's two-sided or not. Right now, the only setting that we're worried about for rasterizer is two-sided versus, back face culling. The state object is ID3D11 rasterizer state, as you would expect. And in here, I do something this is a little interesting. Let me just give you guys a little talk on this. So something I've been aware of, but haven't been using up until now, is there exists for each one of these, or for most of these desk types, descriptors. You can do D3D11 rasterizer desk, and that'll give you a struct, and then you can fill it. But there's also C D3D11 rasterizer desk, and that's actually a class type that encapsulates them and has a few features that sometimes can come in handy. The main one is you can set it up. If you pass it this specific kind of tag structure to the constructor of CD3D11 rasterizer desk, it will construct it with some default parameters. So I can construct one with default parameters, and then I can assign that to just a normal D3D11 rasterizer desk, and then I can pass that in, and it just works. And this can sometimes be a lot easier than having to fill manually all of the different members, especially if you only want to specially change one of them. And after that, it's very simple. Create is just pass it to desk, you pass it to PP as usual. And when you want to set the state, you only got to pass it the pointer to the state. And there you go. You're all done. It's very easy. Note that we're not actually taking this into consideration yet. This was just a simple test to make sure if I if I jam this into our system, it wouldn't screw things up. And it didn't screw things up apparently because my commit message says seems to be working. So the next thing is to use that to enable backface culling control. So in rasterizer.cpp, it's very simple. In addition to the default setup, we make one change. We set cull mode based on the value of this one, cull none or cull back. You can also cull front if you like, which is useful in certain special techniques. But that's the only change here. And then in mesh.cpp, we've actually got to use this guy here. And what we do is we resolve out a rasterizer. The backface culling behavior is controlled by whether or not the diffused texture of this material has alpha information. If it has alpha, then we want to disable backface culling. That's not always what you want to do, but in our current scene, the only ones that have alpha are also the ones that we need to draw from both sides. So we resolve out our bindable, put that into our, container of bindables, and we're good to go. And here we are. We are now able to view from all the sides. So, yeah, we're viewing from this side. We're viewing from this side. There's a problem. Can you see the problem? Why is this chain lit? It's facing away from the light, and yet it's being lit. It's lit, fam, and it should not be lit, fam. So what the hell? Why is it that when I look at these guys from the back, they're lit? They should be unlit from the back. They should be lit from the front. Well, the thing is, we're drawing it from both sides, either side we look at it, but the normals are, in either case, the normals are still facing in the same direction. But if we're looking at the back side of a piece of geometry, then the normals they have to be flipped, right? Depending on the exact situation, what you're trying to do, they have to be either reflected or flipped. But they got to be facing in more or less the other direction, and they're not. We're not doing anything about those normals. So it's not a good scene. So to fix normals on the back-facing triangles, you just have to do a little change to your shader. You're going to check the dot product between your normal and the actual position of the fragment you're rendering relative to the camera. So the normal should be generally pointing towards the camera if it's a normal front-face triangle. So a simple fix here is take the dot product between the normal and the fragment position, and if they're pointing in the same direction, that means you're looking at something from the back side, and so you want to flip the normal. Remember, we work in view position in our shader, so the origin is the view position. So that means that the position of the fragment is the vector from the view position, the viewing vector from our camera to the fragment. And then here's the normal. If we dot these together and they're greater than 0, they're pointing in the same direction, which means that this face is pointing away from the camera. We're looking at it from the back side, so we should flip this normal before we do our shading calculations. That's how that works. And it works out pretty good. Now, there are things here. Sometimes you don't want to just negate it. Sometimes you might want to reflect it in the plane of the geometry. And also, sometimes you will want to also do some of that bullshit for your view tangent and your bitangent. Those are things you want to think about. For our situation here, it don't really matter. I'm just going to negate the normal and it's going to look fine. So here we go. Let's give her the old, the yummy test. Looks good from this side. They should be lit. From this side, they appear to be dark. From the back, they are dark. So it is now, the normals are now working properly. Plant. It's lit, fam. Go from the back side. It's not lit, fam. Good. So that is working as you would expect. All right, now a little bit of cleaning up. I create its own shader for that technique where it's two-sided and masked. So now the normal materials are back to not having all that stuff that they don't need. And the way I do that is actually a little interesting. What I do here is in the PS spec normal map, I put a little pre-processor switch in here. So if mask boy is defined, then we're going to add this, and we're going to add this when we compile this shader. But if mask boy is not defined, then this stuff will all be removed. It'll just be our shader that we had from before, more or less. So what I do then is when you compile PS spec normal map just as it is, this isn't defined, so it's just the normal thing without the alpha testing and the normal flipping. But I add a new HLSL shader file here called PS spec normal map. our normal mask. And what it does, it defines that flag and then it includes the original shader here. So here I can do, without duplicating all the code, I just have one version that is the base one. It includes both code bases, and then another one that just defines a mask to specialize it, to enable a part that is disabled by default. And then in mesh.cpp, we have a little bit of change here. So all we do is in the relevant material, instead of, hard coding which pixel shader we use, we check to see if we have alpha diffuse. If so, we use the mask version. Otherwise, we use the non-mask version. That's it. Here, I just play around with some other of our bindables. I try to do them with the CD3D11 classes, and you can see here it removes a little bit of the need to set defaults here and here. A little bit of it's not bad. I just like to say that I've had mixed feelings on these ones. Some of them are kind of jank and they're weird. They don't all follow the same interface. So I'm not telling you guys, we should definitely use this. This is really great. I'm just saying it's a thing that exists. If you want to use it, go ahead. If you don't want to use it, I don't think it's a big deal. And then finally, I just tweak the colors of the plants and stuff. Colors and other sorts of things, specular maps. So here's what that looks like when it's all done. I think now the hue of the ivy here matches the hue of the plants a little better. But it's all personal preference, right? But yeah, now there's one last little thing that I want to just cover you guys here. A little bit of a bonus. Remember I told you can do alpha blending with the alpha channel of a texture, but you can also do alpha blending with basically a constant that gets applied to each pixel drawn in the draw call. So what we're going to do is we're going to create another drawable called the alpha blending pane. Oh no, actually what I do is I just repurpose test plane to use alpha blending. So for the test plane, instead of drawing it with a texture map, with specular and normal mapping, we're just going to draw with a solid color. So that means we're going to replace the shaders with solid VS and solid PS. We're also going to add blender and rasterizer bindables here. While we're at it, we're also going to update the solid sphere drawable so that it has proper blending and rasterizing state set. Because if the other objects in the scene are setting this stuff and this guy isn't setting it, then it's just going to get whatever is left over from the object that was drawn before it, and that might not be what you want. Also add blender back into mesh.cpp. Now that we're going to have objects in the scene setting the blending state, we should have all of our objects setting their own preferred blending states. I changed the interface of Blender now. Instead of just having a bool stating whether or not blending is enabled, it has a bool stating whether blending is enabled, and then it has an optional float setting the blend factor, whether or not there is a blend factor, and if so, what is it. Also some functions here to be able to set and get the blending factor. And then in blender.cpp, we do that stuff that I was teasing at the beginning of the video, and that is, let me see here. Well, we have an optional array of floats, 4 of them, and that's the factors for blending. You can apply them separately to the RGB and alpha channels. We generally want to uniformly scale those values, so they'll all be set to the single float that's passed in here. So when we construct a blender, if it has blending factors, we're going to initialize the array in the optional there, and then we're going to fill it. Fill all 4 of those values in the array with the value from factors in. And then when we set the descriptor for the blending state, we're going to control it based on, well, first of all, if we're blending or not. If we're not blending, we just want the default. That's going to be working for us. If we are blending, we want to set blend enable equal to true, and then we want to check to see whether we have blend factors. If so, we set the source and destination blend to use the blend factor and the inverse of the blend factor. If not, we want to use the alpha and the inverse of the alpha. Note that I can remove all of these because they're actually, all these ones down here, because they're actually being set by the defaults. So they were no longer necessary. And then once you got that, you have your blend state set up with a bunch of options. Now when it's time to bind that, we have to pass the factors in. So they're passed in as a float pointer to an array of 4 floats. And that's either going to be the pointer to the data in our array, or it's going to be a null pointer. So we select it here with a ternary, and then we pass it in here, instead of just passing a null pointer like we were doing before. And then down here, set factor and get factor are pretty self-explanatory. And because the constructor signature changed, we have to change the stuff in our, in our mechanisms here for the whole codex system. Anyways, so we got the new Blender with more options. We got the test plane, which is resolving out our Blender, and it's doing it with blend enabled and with a constant blend factor of 0.5. In app.h, we're going to add a test plane, and here we just set the position of the test plane to the camera position to start off with, because I was too lazy to figure out what position that is and actually set it manually. So I just get the camera position, use that to set the pane position. So here we go. Let's move away here, and here's our blue plane, and you can see it is translucent. We can see through it. It's also being rendered two-sided. Very nice. Beautiful. So there you go. You got your alpha blending after all. Chili didn't lie. So what's better than one plane in the scene? Well, of course, that would be two planes. So we add another plane, and we give it a different color here. You can see the colors are different. I also have the ability for the test plane to spawn a control window with a custom name, not just a name plane. Because obviously if you have two planes in the same view with the same name, you're only going to get one ImGUI window. So here you have the ability to differentiate them, give them each their own control window. So here we go. We have we have one plane, but let's see here. Red plane. Let's move it out here. And it's blue. Dabba dee dabba die. Why is it blue? I said for you to be red. Well, dang. Let's set the translucency on one of these guys. They're both changing. What is this madness? Yeah, this is something I told you guys to be aware of, but if you're gonna resolve out bindables, you're going to be sharing them, but some things you don't want to share. Some objects, for example, you want them to have their own individual transforms, for example. Or in this case, we want them to have their own individual material constants. All right, so now we have separate boys here. Let's see. Let's separate the planes. And yes, it is red. Beautiful. We have success. Can we set the transparency independently? No, we can't. All right, yeah, because that's because they're still sharing the same, I believe, Blender. But anyways, forget about that. That's not important. What's important is that this is actually all farked up. Look at it. Can you see that this is not weird? Well, let's look at it from the other side. You see, from this side, it's very clear. You've got the red, which is being blended over the scene. And then you've got here the red being blended over the blue being blended over the scene. And then here's the blue. That's what you would expect. But if you look at it from this side, the red completely disappears. The blue just takes it over. It's like it doesn't exist. It's like it just got cut off here. Why is that? Well, it's similar to the problem we had at the beginning of the video with the plants and the case of the disappearing vase. And the reason why is because, of course, Z values. So we draw this one first. It's in front. Then when we draw this one, this fails the Z test, and it never gets drawn underneath here. And this is the basic issue that I was actually alluding to at the beginning of the video when I told you that the concept of alpha blending is simple, but in practice it can be a giant pain in the dick. Because basically, this is a problem. When you've got a lot of translucent objects in a scene, this can become quite a problem. And the main way of doing it is the thing I told you that we don't like to do, which is sort your objects, draw from back to front. So what I think most game engines are going to do, because it's the simplest and the most performant thing, is you draw all of your normal non-translucent objects. You draw them just, in the proper order for best performance that you can do, which is often drawing front to back, opposite of Painter's algorithm. And then you draw your translucent objects separately, sorting. But of course, as we know, sorting cannot fix all problems with overlapping. And there are many techniques that have been, examined, stuff like depth peeling, with multiple rendering passes, using linked lists of fragments, using weighted averages, stuff like that. There's lots of techniques, but none of them are perfect, and all of them are slower. Many of them are incompatible with techniques like anti-aliasing, so it's a big problem. No one has really found the one solution to it. But for right now, I think for most people, it's safe to say that if you're going to be using translucent objects, all you really need to do is just draw them separate from the other stuff, sort them, and then just, don't make scenes where that is going to be an issue. That's about as deep as we're going to go into it right now. But I just wanted to introduce to you the idea of the alpha blend order conundrum, and also wanted to show you guys how you can implement that alpha blending with a uniform blend factor. But that's going to about do it for today. In the next video, we're going to change gears a little bit, and we're going to address a problem that I've been avoiding. I do that a lot, right? Basically, you guys, if you run this program yourself, you'll notice it takes a hell of a long time to load, and that's mainly due to how slow our current texture loading code is. I mentioned it before, but in the next video, we're going to replace that with stuff from the DirectX toolkit, a subset of the DirectX toolkit called DXTeX. We're going to use the image loading utilities that they have available. It's going to make our images load faster. It's going to be cool, and it's going to be a really cool little use case of how encapsulation is actually an essential technique for serious software engineers. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.